Alright guys, I wanted to go over some things on designing common emitter amplifiers in preparation for Lab 4 and Lab 5 for 340. So a BJT can be used to make different sorts of amplifiers. So when you see one like this, where your input's on the base and your output's on the collector, that's a common emitter amplifier. The emitter is common to both, this is the emitter. The emitter is common to both the input and the output, and we'll use them in Lab 4 and 5, and in Lab 5 we'll also use one more type. When we're talking about these amplifiers, often we refer to biasing them. So I wanted to go over what that means and how we can do that and why we need to do that. So there are different regions that a BJT operates in, and what we're shooting for is the active regions. In the active region is where a BJT is going to amplify. If we are in the cutoff mode, then our VB is not high enough. We need to have a voltage drop from here to here to turn it on, and if that's too low, we're in cutoff, there's no current flowing, and we're just like an open switch. These two terminals are like an open switch, and that's not a very good amplifier. It would just be sitting here at 9 volts because no current is flowing. If, on the other hand, we're in saturation, then this, especially if we're in like heavy saturation, not when it first approaches, but this is like a closed switch where all the current is flowing, and then we have a really low voltage here because, you know, most of it drops over there. So we'd have, let's see, RE, it would be like a voltage divider, so we'd have RE over RC plus RE times 9 would be our V out in saturation. Okay. So what we want to do is we want to identify our rails. We want to identify what's the highest value that V out can come to and what's the lowest value V out can come to. So we already said that V out can, if there's no current flowing, then V out can be at 9 volts. Okay? And we said that happens during cutoff, right here in this cutoff phase. Okay. If we are in saturation, we can be down lower. We can be here, which if our RC is bigger than our RE, much bigger than our RE, then we can get pretty small. We'll quote approach, you know, 0. So if we're trying to do a high gain amplifier, it'll be closer to 0. So these are the rails, meaning we can have an output approach these rails without distortion. So we could have some sort of nice sine wave. So what happens is we have something called voltage swing, something called headroom as well. So the voltage swing would be like the amount of output you can achieve before distortion occurs. So you can see in this top graph that the top of our wave looks great. The bottom is clipped. We hit that rail. You can see here that we've hit a bottom rail and it's distorting. And something to think about, is this in saturation or cutoff? Here we're clipping on the top first, and our bottom looks smooth and great. So we've got some distortion here, and when we talk about headroom, that we want to have, you know, maximize our headroom, it's where we're trying to set our DC bias to be in the center of our rails. So when we talk about trying to be in the active region, when we bias our transistor, we want to center our output here, the DC value of our output, to be sitting about the middle of our rails. That way whatever input comes in, we will amplify it, and we would want, if we do achieve distortion, you know, if we have a really large input, then we want to be clipping on the top and bottom at about the same time. So we're maximizing the amount of good output we have before we hit distortion. So that is why we want to bias these properly, so we can have the most outputs that are just in the active region without hitting saturation or cutoff. So now let's talk about how we design this amplifier. So typically you think about your gain, if there's a specific gain you're trying to achieve. So in Lab 4, you guys have been assigned the task of 5 volts per volt. It's unitless because it's V out over V in, but we often say volts per volt. And this demo that I'm going to do, I'll just do at 8 volts per volt. Because if I just do one at 5 volts per volt, that's no fun for you. It's like showing you the answer, take away all the fun, all the challenge. So I'll just kind of show you real quick through this 8 volts per volt problem, and you guys can just see the feel of how to do it. So our gain equation is roughly RC over RE. There's other things, but this is a good starting place. I'm going to make my RE 100. I'm going to make my RC. I don't have 800 in my kit, but I do have 820. I'm going to actually go to a new slide so we're not so messy. So let's say we make him 820, and let's say we make him about 100. Okay, so great. I've already started to design this thing. This will get me roughly a gain of 8, hopefully, and we'll play with it in LT Spice and see how that works for us. Now, what are these resistors here for? It's a little bit convoluted. When we start biasing common collector amplifiers, it's a lot more straightforward. But here we're going to be trying to set a voltage. We're going to think of R1 and R2 as a voltage divider because the impedance looking into this transistor will hopefully be bigger, so it'll be a little more negligible. We can just kind of think of them mostly as a voltage divider, especially if we make RE big enough. But we'll talk about input impedances of transistors in a little bit down the road. Okay, so we've got a voltage divider here. We need to have a voltage here so that this transistor turns on, and we are controlling this current. So we want to have the appropriate amount of current through this resistor to get this voltage where we need to be, which is in between our rails. So step one is we should think about our rails. So we already said that if we're in cutoff, then no current will flow. If no current is flowing, then we will be at 9 volts. So our upper rail, 9 volts. Our lower rail would be when we're in deep saturation or heavy saturation, and this is functioning as a short. And in that case, we would have a voltage divider. So we would have 100 over 100 plus 820 times 9, which is about 1 volt. Now, if you are, remember, if you're designing for a gain of 5, you're going to have a different ratio and you'll have a different lower rail. So my rails are going to be about 1 volt to about 9 volts, which means I'm going to design, I want my center to be about 5 volts. And that means I want the DC value of this output to be sitting at 5 volts. Then whatever comes in on my input and I amplify it, I want it to be centered at 5 volts so that I have good headroom and I can start clipping at the top and bottom about the same time. All right, how do I do that? So now we're going to think about the voltages and everything involved. So this guy here, we think of it as functioning pretty much like a diode, and let's say it's 0.5 or 0.6 or 0.7, some amount of voltage drop here. So I'm going to say 0.6. I need to know my current through here, because if I know this voltage drop plus my voltage drop across here, then I can know the voltage that I need here, VB. Because VB is going to equal my VBE plus my current times my resistor. And technically, our current through our collector and our current through our emitter are not identical, but they're certainly close enough for our purposes. So now, what current do I need here? And the answer is, I want this to be sitting at about 5 volts in my example. So that means I need a 4 volt drop across RC. So I'll come over here and I'm going to just do Ohm's law. I'm going to say, well, if I need 4, then I'm going to say 4 volts over 820, and I'm going to solve for that current. Okay? And then whatever value that is, I'm going to multiply it by my resistor. Let me pause it for a second. All right, we're back. So we looked at our curve and it got all funny, but hopefully we are not funny this time. Okay, good. Now it's behaving better. Let's look at our output and our input together. Okay, so our output, we have a peak to peak of, that was wrong. I did that wrong. Okay, let's look at our output and our input together so we can get a feel for our gain. So the peak to peak on our output is 4.6 volts. And the peak to peak on our input is about 0.6, which is right because I put in 0.3. So if we do 4.6 divided by 0.6, so we can come back in here, do a little quick math, and we've got 4.6. So 4.6 volts divided by 0.6 volts. We've got our V out over V in, and that's 7.7 volts, which is great because we were going for a gain of 8, and that's within 10%. So that is awesome. So a couple things to point out. One that I haven't mentioned yet. This guy right here, he is important. He is super important. If you are building one of these capacitors and you're making all this effort to bias it, meaning you're trying to get the DC level here to be just the right value so that the current comes through and gives you just the right DC value here, so you're centered between your rails, so you're avoiding distortion. If you don't have this guy on here, whatever you apply as your input is going to affect this DC bias and change it and mess it up. So this capacitor helps you isolate your DC bias that you're establishing from your input signal, whatever your input is. That's why you can see here on an LT Spice that, you know, your DC value of your input can be really different than the DC value of your output. And if we didn't have that capacitor here, let's just look at what happens. Okay, so let's take him off. Oh, and we're doing that funny thing again. Here we go. All right, so we're going to take off this guy. Let's see what happens if he's not there. And we're going to run it. And now we're going to look at our output and we're going to say, oh, we are in cutoff. Our output's just at 9 volts all the time. So even though we might have designed everything right where we should have gotten the right bias and we should have gotten the right gain that we wanted, if you don't have this capacitor here, then it's going to throw off all that work you did for your bias and it's not going to work properly. So please remember, this was an example with 8 volts per volt, so your values will be different. Your R1 and your R2 will be different, your RC and your RE will be different, and the other thing is this C1 can be used if you want to determine your corner frequency. In lab 4, you're going to be looking at an upper corner frequency and a lower corner frequency. So you're going to give some thought about which capacitor does what. You know, if your C1 will govern your upper corner frequency or your lower corner frequency, the same with C2. And so you'll actually be picking this value to help you with a specific corner frequency. I just threw in a value for now during my bias stage to isolate the DC. Hopefully this has been helpful, and good luck on lab 4.